Well, thank you so much for the kind invitation and the very kind introduction. It's my first time in Kansas City, and it's been a wonderful first visit, and I thank you all for the kind welcome. So what I'm going to talk about today is using nuclear techniques to analyze art, which really is a sort of side hobby of what we do. What we mostly do in the science laboratory at the University of Notre Dame, I've learned the Hoosier expression, is actually to use the various techniques that I'm going to talk about to really study stars. So nuclear astrophysics is my main field, and so please see this as coming from a physicist. I'm not an art historian, so just keep that in mind. I'm just a sort of interested physicist. So what is this all about? And it basically comes down to answering the question is, what is the value of a work of art? Ultimately, every piece of art is a piece of art. How much is it worth? That is a totally different answer, and that's when you go into this whole question of forgeries, and specifically also, but more importantly, is how do specific works of art or archaeological finds fit into a larger picture? And that is what we mostly do. So what I'm going to talk about is going to concentrate on both areas. What we work on at Notre Dame is mostly trying to understand how an archaeological find or a work of art fits into the larger picture. We tend to shy away from authenticating works of art simply because of the legal implications behind that exercise are way beyond anything a university wants to take on. But the techniques are the same, and so I'll explain that as we go along. So this really is sort of a talk that tries to explain what a laboratory that is really dedicated to nuclear astrophysics, and I promise I will not talk about nuclear astrophysics tonight, actually will provide to the world of art or to the world of archaeology, or at least our attempts to. And it all really comes back to this following statement from Aitken in about 1978. He said, within an archaeological artifact, there is a record to which an archaeologist, or one can say an art historian, is blind, but which a physicist can hope to read. And emphasis is on hope. Because we can try, we don't always succeed. And one of the things that I'd like to emphasize, and I'll probably say it several times over a talk, is we can only provide a piece of a puzzle. The full answer really comes from all the different pieces, what the art historian says, what the physicist says, what perhaps the chemist will say. All of those will give you a picture of this work of art or its provenance or whatever. It's not just generally one single answer. So what I'm going to talk about are really two specific techniques today, PIXI, which is proton-induced X-ray emission, and AMS, which is accelerator mass spectrometry, which is more sort of my specific field. But I'd like to point out that there are many, many other science-based techniques that can be used and that are used. They have their home in nuclear physics, in atomic physics, in biology, in chemistry, all bring a certain answer to the table. But let's start with what is always the most fascinating, which is, let's start with the forgeries. Why is all of this important? Well, I'll go back to one specific case, but there are many, many others that one can look at. And that is fall 2011 in Cologne. They started a trial for what is probably the largest forgery case in Germany. You are looking at up to 53 paintings by 20th century masters, including Campendonck, Pechstein, Fernand Léger, Max Ernst. Scam started in the 90s about. The paintings are supposedly from two collections, the Jägers collection and the Knops collection. I will come to that later. But so these were collections that are referred to by major auction houses that actually never existed. The interest in all of this is that you're looking at works of art that probably overall totaled over 30 million euros in sales, and those are only the officially recorded ones, all of which are fake. And the interesting thing is, once we get to it, the signs were there, but very few people actually really bothered to look at it. As I said, millions of dollars were lost, and actually in the background you can see, and we'll see this picture again, one of them, which is landscape with horses, sold for 700,000 euros to Steve Martin, who thankfully resold his just before the scam came out. at least for him. But here is one of these works of art. This is Red Picture with Horses, Heinrich Campenong, famous work. I will come back to this one because this is the one that actually started this whole research. I stole this from Sotheby's website. I actually stole it last week, and you can still see it. It was sold a few years ago. Sale price was $1.1 million US. It was authenticated as being a real Max Ernst. It's a fake. One of the people that actually authenticated, and that is totally innocent in this, he was a sort of bystander, but insisted that his authentication did not need any scientific research, which is why I'm bringing this up, is Werner Spies, who's one of the big specialists on Max Ernst. And it's interesting to see, this is a statement that I found actually last week, the Beltracchi, I'll come to that in a second, his authentication of all of the Max Ernst works of art that were sold turned out to be completely fakes. Not his evidence, he was convinced that they were true, but ultimately they were all fakes. And it really completely ruined his reputation. And actually they just put on at the Albertina in Vienna an exhibition that was trying to sort of rehabilitate him. But that's just to show that it's not only a question of money. There is also a lot of personal stories that are involved in these fakes. So the problem is who? Ultimately, the fake painter is Wolfgang Beltracchi. His wife Helen and her sister were involved. He painted all of these paintings. He's a brilliant painter, by the way. I don't want to detract in any way from the brilliance of his work. But they claimed that all of this collection that they were selling was inherited from Werner Jägers. This is this famous Jägers collection. There was also the Knops collection. And that he had actually bought them all from Flechtheim. Alfred Flechtheim was a famous art dealer in the 1920s in Germany. When he fled, most of his collection disappeared, and not all of it was documented, only some of them were described in various catalogs. And so they sort of based this whole story on the idea that Flechtheim was friends with Jägers and with Knops, and that they had acquired these works of art. These works of art were then later authenticated, but never scientifically analyzed. This is just a short list of some of the works of art, and some of them are major. Interestingly enough, once all of this sort of started out, and it started out with this work of art, the Red Picture with Horses, which was sold for 2.9 million euros to a company in Malta called Trusteco. They didn't trust the provenance. They actually asked art historian Andrea Firmenich to analyze the work. She actually sent the work for scientific analysis, and this is where I'll go into the nuclear physics part. And what they actually saw is that some of the pigments that were used, which was in part titanium white, did not exist in the 1920s. So it could not have been painted in the 1920s. But not only that, they actually found on the back of these stickers that pertain to come from the Flechtheim collections. These stickers were totally fake, did not even resemble the original Flechtheim stickers. So that's the degree of which people did not look at what they were looking at. Another hint, there were 4 paintings, I only found 3 of them. There's an André Derain, a Max Pechstein, and a Fernand Léger, all painted at different times, yet they were all framed in wood from the same tree. Again, I will go back to this, but you're looking at over $30 million or euros that went in this. So what science showed, and this is where I'm going to sort of take off from the art side and go into the science show, is that many of the different paints that were used were actually not available at the time. So what is this based on, and how does nuclear physics fit into this sort of larger picture of art forgeries? This is where we come to one of the techniques that I'm going to talk about, which is X-ray absorption and fluorescence. And the idea behind here is that all atoms basically are constituted of a nucleus and then electrons in outer shells. What happens if I excite these electrons? Let me try and see if this works, yes. So I excite these electrons, they transition into shells, and then as they transition back, they emit an X-ray, or they emit light in the visible. And if I actually know this, I can actually characterize exactly what type of element I'm looking at. Here we've got hydrogen, and specifically these are in the visible. I have 3 lines, one in the red, one in the blue, and one in the violet, that are called the Balmer series, but that are specific to hydrogen. So if I'm looking at a spectrum in the visible of something, and I see these lines, I know that I have hydrogen. This is the same, and this can be characterized for a lot of different elements. If I look specifically here, I can have specific lines that are in the zinc, the copper, the lead. Those are totally independent of where this material is. So I can do this analysis, and I can have tables that tell me, for lead, I should expect specific lines, at specific places. And so one of the ways of doing this type of analysis, which is actually called X-ray fluorescence, you actually have a small X-ray tube. You have a camera that actually documents the physical spot that you're analyzing. And then you have a detector that detects your X-ray, and you come up with a sort of spectrum like this that tells you some of the components that are in the sample. Each of these samples are specific, but the materials that are in them will always give up these lines. How does that help me? If you look here, and I'm not asking you to remember all these chemical formula, but if you look here, each of these are some of the more typical pigments, white, yellow, red, that have been used, and I've got, I think, greens here, blues here, and blacks here, that were used over the ages. All of these have specific elements in them that are specific to this specific element, like titanium white will actually have titanium. None of the other white pigments will actually contain titanium. Actually, titanium white is only one of the more recent pigments. So if I actually analyze a picture and see a titanium line, then it actually is an indication of what type of pigment was used. How does that help me? Well, if we look here, this is just the sort of genealogy of time you have up here and when specific paints were used. You can see that some of them were used from the Greeks up to now. This is the yellow ochre. Some of the pigments were only used more recently. Some of the, like in the blues, the Egyptian blues were really only used in antiquity and never again later. Some of them were used over long periods of time. So by knowing that, by knowing the pigment composition, by now being able to actually analyze a work of art, I can get an idea of what types of pigments were used. They won't necessarily tell me if something is a fake, but they can give me this piece of a puzzle. They can give me an indication of what I'm looking at, and I'll give you a typical example. Typically, Amedeo Modigliani lived from 1884 to 1920, is an artist that was faked many, many, many times. But if we looked at one picture, this is called Portrait of a Lady, and it was tried to be introduced in a major exhibition on Modigliani. And what people and forgers try to do is actually introduce major works of art into exhibitions, because once they have been in a major exhibition and have been authenticated, they generally get this seal of being true and can be sold. What they actually found when doing this type of analysis is they found traces of cerulean blue. You can actually see tin and cobalt lines in the paints of the blue here. And this is a pigment that Modigliani never used. There are actually some other pigments. There's also a green that he specifically used that they never found here. So this was an indicator. Again, it's not going to tell me this is fake or not, but it was evidence enough for the exhibitors to not take this painting, and later on it was actually proved to be fake. But so you can actually, without damaging this painting, by simply passing over it with some X-rays and looking at the X-rays that are emitted, as each of these X-rays are specific to an element, they give me some information. And if I sort of correlate that with the pigments that are used and their composition, I can get an idea about if this is fake or not. But this is not only a technique that is used to authenticate works of art. Very often, works of art, people are looking to attribute them. If I'm looking here at the Breviarium van der Berg, which is actually in the collections of the Van der Berg Museum in Antwerp, it's a breviary with beautiful illuminations, and 3 different artists are known to have illuminated this. Simon Benning, Gerard Horenhout, and Jan Provoost. And what they were trying to do is find out which of these various illuminations was attributed to who. And what they were looking at was specifically this light green that you can see here and the light green that is used here. And using this same technique, what they actually found, if you look here, is that the compositions for both the St. Michael, I will go back here, so St. Michael is here, and the birth of the Virgin is here. And if you look at it here, the compositions of both of these are identical, which says 2 things. That not only were they painted by the same, which is in this case attributed to Jan Provoost, but that he probably painted them at the same time. Because in those days, painters would always mix their paints themselves. This was not an exact science. So from mixture to mixture, even though the paint would be probably the same color, the exact composition of the paint would never be exactly the same. Because we can see the exact same concentrations for all the elements, they can actually attribute it that it was probably painted and at the same time from the same batch. So again, this has nothing to do with authentication, but it really has to do with assignment. Where does a work of art fit into? Where does it come from? In the third picture here, if you look at the darker greens, there's darker green here and the dark green of the curtains here, they actually compared those to a third painting that they knew was not from Jan Provoost, and you can actually see that for the 2 first, which are actually attributed to Provoost, the composition is pretty well the same, with the exception of the lead that you can see here, which probably comes from the fact that there's lead white underlaying the cape that one can see here. But the one that is in the back, that is definitely attributed to somebody else, has a totally different composition. So again, that's the type of information that I can get there. So, knowing about this technique, how does a nuclear lab fit into this? And that is because we use a slightly different technique. So in the technique that I've talked up till now, you use an X-ray to excite electrons, and you look at the energy that is emitted. What we actually do is we use protons. So for that, we actually need an accelerator that will accelerate these protons. And the principle really is the same. As these protons plow through the material that you're looking at, they're exciting the electrons. As the electrons come back down to their rest position, they will emit X-rays. So the signal that we see is exactly the same than the signal that you would see with thermoluminescence. The only difference is that because I'm actually producing X-rays with an accelerator, I can actually vary the energy, which means that I can actually vary the depth into which I go into a piece of art, which gives me a much better resolution. The disadvantage, I need an accelerator, which is large and which is unwieldy, to say the least. But the advantage is that I get a much better resolution. But obviously, it is also more complicated to use than a simple small X-ray gun. So what is the principle behind there? So this is actually the lab at Notre Dame. We have actually 3 accelerators. The one that you will see in an animation in a second that we use for analysis of works of art is this, our largest accelerator. We actually have our newest, and as I say, most of the work that we do is actually related to nuclear astrophysics. But the fun thing is we get to do a little bit of work on the side which has to do with art and archaeology, and that actually is the one that probably excites the students the most. So it's a win-win for us all. So if you look at this, you actually can see a work of art. This is an animation that was made by one of my students. He insisted on putting this picture there. So you actually see, this is the ion source. This is where we actually start off the beam that we're going to be using. You have a hydrogen molecule that we actually gets injected into the accelerator, gets accelerated. This is the accelerator itself, which gives the protons the energy that we need. We then bend the beam and bring it all the way to the Mona Lisa, although we have not done the Mona Lisa. But what you can actually see is as the proton passes through matter, it actually emits this X-ray, and the X-ray will always be specific to the material that emits it. So let me go back to my talk now. Here we go. And so the final setup is actually the following, which is the typical setup that we would do for any piece of work. So you have the end of the beam line that is here, you have a very, very thin foil at the end of this copper piece that actually allows us to be in vacuum behind here, and the proton beam that comes out here. And the protons will actually plow through the artifact, and as they plow through, they will excite the electrons, and as these de-excite, they will emit the X-rays that we're looking for. And this is the detector that will actually see the X-rays and give us a spectrum of what we're looking at. And we can use this, as you can see here, this is an icon of Christ. This is the one that we actually used. This is one of the pictures that we used for the Physics Today article that was made the front page. And some of our colleagues kidded us that only we could get a picture of Jesus Christ on the front side of Physics Today. To which I added, yes, and we were not only doing that, but we were shooting at it with a proton beam. But so we were actually looking at the composition here of the various paints for the anthropology department. Here we are doing analysis of Mesoamerican figurines, specifically looking at the different glazes that were used. And here actually we were analyzing dinosaur teeth. It's a big block of black, but it's actually fossilized dinosaur teeth, and we were looking at material that you can find in it. And what was interesting is that you have relatively high concentrations of uranium, which gives some indications on where they fed and things like that. So that was quite interesting. So the way that it works is you have your proton that goes through, you have an electron that is excited. As it de-excites, it emits this X-ray. And for each of the materials, we have specific X-rays, and this is the type of spectrum that I get. So again, this is a piece of information on the whole composition of the elements that I see. If I can then relate that to what I know about it, I can extract information. Typical example is here, this is Ishtar, statue, a goddess of love that is in the Louvre. And for a very long time, the curators actually thought that the eyes were simply red glass. It turns out that they're actually rubies. And you can actually see the setup here again. The proton beam comes here, hits the eyes themselves, and the X-rays are emitted. And this is the type of spectrum that they were looking at. The interesting thing is if you're looking at rubies, this is the formula. Again, I will not ask you to remember it. I don't even ask my students that. I don't do it myself. But the interesting thing is, once they discovered that they were rubies, what they were looking at was specifically ratios of An to some other elements that are in there. And specifically, An versus chromium. And what you can see here is that there had been an analysis done previously of rubies from 3 different mines, one in Burma, one in Sri Lanka, and 2 in India. And what you can see is if you actually sort of look at An versus chromium, they sort of clump together into regions. And these are specific to the rubies that are mined in those regions. And what they then did is they compared the rubies here and the composition of the rubies here, and you can actually attribute that, and you can actually see the dot here. So what that actually indicates is that the rubies that were used for this statuette that was found in Babylon most probably came from Burma. Can I say it with 100%? No. But it is certainly a very strong indication. Why is that important? Because that starts to give us some information on trade routes. It allows us to get an idea of when this statuette was made, what were the trade routes that were in use, where did the various rubies come from. It's, again, a piece of the puzzle. We're not answering the whole question. And that's, again, something that I always want to stress is we just bring a piece of information to the puzzle. We don't finish it. But another example, this is also work that we've done, is looking at copper from Native American settlements. And the interesting thing is if you're looking at copper, depending if the copper is from European or from American origin, the lead versus antimony content and the lead versus silver content is different. And so by looking at the various copper, and these were very often, they were copper that they used in weapons and things like that. If you actually look at it, you can actually classify where the copper came from. And that actually is an indication, again, of what type of trade was done at the time and the native sources. So where they actually did certain tribes actually use copper from native European sources, or did they use Native Americans? And that again is a piece of indication, it's a piece of the puzzle that allows us, or when I say us, certainly not the physicists, but the anthropologists, to better understand the trade and the movement of population and things like that. So again, this is, and that's what I'd like to stress, is as interesting as the analysis of art forgery is, sometimes actually looking at the history and how does an artifact fit into a larger picture, I think personally is more rewarding. The other question is more often linked to how much is something worth, which is interesting and certainly important, but here you're sort of trying to puzzle together the movements of population, trade routes, things like that, and that's what these techniques can bring. And the beauty is that the tools that we use for nuclear astrophysics, the tools that we use to study stars, can actually be used to really study these artifacts and things like that. And as I say, where we tend to keep away from authenticating artwork, we tend to work more with the anthropology department on origin of artworks and things like that. But another piece of work that is of interest too, and that is certainly of interest more here, is, and that's something that we've started, is the analysis of the contents of ink. So what you can actually do with this technique is actually pinpoint specific points on a parchment and actually look at the composition of the inks that were used. So inks were always mixed by people who were writing themselves. So the general composition can change, but the general formula that they would use for their ink would be the same. But there's actually quite interesting work that we certainly didn't do, but they were done in Italy, of analyzing documents from Galileo and the ink that he used, and you can actually retrace his financial situation with the quality of the inks that he was using. And so you can really get an enormous amount of information from this type of analysis that is totally independent from is something true or not. You can really get a lot of information, and that I think is absolutely fantastic. Another technique, so I hope that this has given you a little bit of an idea of what PIXI is, which is this proton-induced X-ray emission, which is totally non-destructive. But this only gives me an information on contents. What are the elements that are in a specific glaze, in a specific paint? That's the only thing I don't know anything about age, except if I can relate it to when something was used. But another technique, and something that goes back to a statement from Rasmus Nierup, he was actually the curator of collections in Stockholm, I believe. I may have that one wrong. But what he said, he was very frustrated because he had to reorganize the collections and try to order them by time. And what he said is, everything which has come down to us from heathendom is wrapped into thick fog. It belongs to a space of time we cannot measure. We know that it is older than Christendom, but whether by a couple of years or a couple of centuries or even by more than a millennium, we can do no more than guess. I beg to differ. This goes back to the statement right at the beginning that says that there is actually a signature that we can analyze. Not everything. Again, we have to be very specific. We're not looking at a one-size-fits-all. But there is actually a signature there, and what I'm looking at is mostly what is called trace elements. Most of the artifacts that we see certainly do not have necessarily rubidium or thorium or uranium in any quantities that could harm us or that we can easily measure. But as trace elements, most certainly, at the level of what I will refer to as 10 to minus 12 to 10 to minus 13, so one atom in 10 to the 12 or in 10 to the 13, you will find the full table of isotopes. They are there. They're naturally there simply because of where this was produced, how it was produced. And so if we can read this signal, and if we can retrace it, we might be able to get some information out of it. The beauty of it is that all of these are what is called radioactive, which means they only live for a specific amount of time. Everything ultimately wants to become stable, but we only have about 270 stable elements. Those are our constituents, and there are 3,000 and over of radioactive elements. Most of them short-lived, but some of them very long-lived. Potassium-40 is actually older than the solar system itself. So are some of the uraniums. Those are present and they slowly decay with time. If they've decayed very fast, they're probably not there anymore. Some of the shorter ones, carbon-14 I'll get to, that's the one that I'll discuss in more detail, has a half-life of 5,730 years. What is it that I refer to as half-life? This is something that is a purely nuclear property. It is not a human property. What it means is that if I have 1,000 atoms of, let's say, carbon-14, then 5,730 years later, I will have exactly 500. 5,730 years later, I will have 250. One half-life exactly halves the amount of atoms that I have, which is very nice, because that means that if I know how much I should have had at the beginning, and I know how much I have now, I can actually relate that to age. I cannot do that with a human population, because in a human population, the decaying, if I may say so, is absolutely related to time, i.e. the longer one lives, the more likely one is to decay, if I use it in this term. So it is really a nuclear property, but it is a nuclear property that is extremely useful, because it allows me to actually have a very, very precise clock. And I'll come to this clock. How does this work? I'll promise not too many formulas. I will keep that to very, very few, but this is what is generally referred to as the radioactive decay law, which says that the number of a specific atom at a given time depends on the number of initial atoms that I have and an exponential decay. And what you can see here is if you have 100 carbon atoms at the beginning, over time they will decay. This is the half-life. And the daughter nuclide that it decays to will actually increase. This is for 5,730 years. The beauty is that depending on the radioactive isotope that I use, I can actually do certain time scales. Specifically here, for carbon-14, I'm looking at history and archaeology. But if I'm looking at something that has a half-life of 713 million years, I'm really looking at archaeology and anthropology. This is the uranium-lead series. Or if I'm looking at way older, the rubidium-87 law, there you can go into the billions of years. Each of these is specific to an age range, and obviously I can't use them all because it depends if some of the material is in there. So how does this work? How can I actually use this? The basis for the carbon-14 method, and the basis for a lot of these methods, is that actually carbon-14 is produced naturally. It's produced by cosmic radiation interacting with nitrogen in the atmosphere. And ever so often, once in a while, there's a neutron capture which produces carbon-14. The carbon-14 in first approximation has been constant over thousands and thousands of years. There is a correction that one has to bring to that, but in first approximation, you can assume the concentration of carbon-14 in the atmosphere is relatively constant. It gets absorbed, like all the other carbon, into living organisms, wood, tree, animals. And as long as these organisms are alive, the amount of carbon-14 that decays gets compensated by the amount of carbon-14 that is taken up. So I can actually measure the amount of carbon-14 that a human being has, and assuming that the carbon-14 concentration in the atmosphere has been the same, if I can measure it now, it should have been the same 6,000, 7,000, 8,000 years ago. That is my starting point. That's the zero time of my clock. Once something dies, or once we die, there is no uptake of fresh carbon-14, and so the only thing that happens is that the carbon-14 will decay. This is where the beauty of the radioactive decay law comes in. I know how much I should have had. I know how many I'm counting now. Therefore, I can deduce the time, which actually is hidden in this beautiful formula that is here. Again, this is the last one I'm showing, I promise. It actually, time is simply related to the radioactive decay constant, which is known to a high degree of precision. And the only thing that I have to know is the number of carbon-14 atoms that were initially in the sample and the number that I have, that I'm measuring now. This I can deduce, I have to know, I have to have measured it at some point, either in something that is modern or we have to have done estimations, and this I actually measure. Once I know this ratio, I can relate it to a time. So how do I do that? This is where accelerator mass spectrometry comes in. There are really two methods to determine the concentration of a given radionuclide, i.e. something that is radioactive, in any material. One is measuring the radiation that is emitted as it decays. The reality of this is if I take 1 milligram of carbon, that contains about, if I take a modern time, about 6 times 10 to the 7 carbon-14 atoms. You're looking at about 1 decay per hour. There's nothing I can do about that. The only thing I can do is take more material. Archaeologists tend to disagree with me on that one, because if they spend thousands of dollars and years digging up something, they generally tend not to agree to give over half the artifact that you have actually found. So they tend to even think that 1 milligram is already too much. But that limits my statistics. So I can either wait a long time or not do the measurement. The other way of doing it is counting the number of atoms themselves. So if I know that there are still some carbon-14 atoms there, they have mass that is 14, if I can separate them out from everything else, then I actually have the same answer. That's where AMS comes in. This is where you can actually see an example. If you're looking at 6 times 10 to the 5 carbon-14 couples in an original sample, if I'm looking at accelerator mass spectrometry, I'm looking at something of 1,000 counts in 2 minutes. That's statistically what I would be looking at. If I'm looking at low-level counting, I'm looking at 1,000 counts in 14 years. So 2 minutes versus 14 years. For a statistics, this is about a 5% error. So with this technique, I have 4 orders of magnitude of improvement. So how do I do this? How does this work? Traditionally, a mass spectrometer is you have an ion source. That's where you put your sample material in. So you basically have your artifact. You extract your few milligrams of carbon material that you generally turn into graphite, and you put it in the ion source here. And then you give it a certain charge, and you bend it through a magnet. The magnet will always bend as a function of mass over charge. So if I set this to mass 14, I should be able to see my carbon-14. The only problem is nitrogen-14 has also got mass 14. And nitrogen-14, as you will see, has got orders of magnitude more abundance. So what I need is a needle in the haystack technique. I need to be able to go into that mass 14 haystack and extract my little signal. That's where we actually replace the detector with an accelerator and some more magnets to get a better resolution. And the way that it actually works, the way that accelerator mass spectrometry works is the following. This is the setup at University of Notre Dame. So we actually start off with the ion source. So this is where we take our sample, we basically transform it into graphite. So we burn it, we extract the carbon, we put it in the ion source. There it gets accelerated. It's the same accelerator that we use to produce the proton beam. But in the case of PIXI, we would use this beam to simply excite the material in what I'm analyzing. Here, what I'm actually doing is I actually have to take a little bit of the material that I'm analyzing, and I'm actually really setting all my equipment to my mass 14 so that I can actually extract this information and look how much carbon-14 is left. The way that it works is the following. So you put your sample in the source itself, and if we look here, this is what actually happens, is there is a cesium gun that bombards the sample, and you can see that everything, including the kitchen sink, gets sent out. There is a charge here, and you start producing a beam, but it's a beam of everything, including the kitchen sink. So I need to get out my mass 14. The way that that works, and this is just to illustrate it, is if you look here, this is a logarithmic scale. This is my contemporary carbon-14 peak, which is at about a 10 to minus 12. And if I look above it, this is what my natural background is, 10 to minus 4. So you have 8 orders of magnitude that I have to separate. 8 orders of magnitude in accelerator mass spectrometry is actually nowadays relatively easy. With this type of technique, I can take a bottle of bourbon, bad bottle of bourbon, pour it into Lake Michigan, and I can actually measure the concentration. We have actually been able to go even further. We can take a mini of bourbon, pour that into Lake Michigan, and that is actually what AMS, the concentrations that are measurable with AMS, that is the lowest levels we can get at this point. But that's pretty good still. I apologize to those of you that like bourbon. My students traditionally always do the example with Belgian beers, so. But so the way that it works is by continuously separating out what I'm looking for, really to sort of look for the needle in the haystack. This will be the next sort of magnet. So you can see the sort of kitchen sink that is appearing here. And every time I pass through with this filter, I'm actually throwing out some of the material. And as I go along, I get something that is purer and purer and purer. Every time I'm throwing away orders of magnitude of material. This is actually the interior, oops, sorry for the repetition, the interior of the accelerator. So you actually have your beam that comes in here. You have these chains that bring up the charge to the accelerator. This is really like your physics ABC, those old accelerators that you had in physics class where there's a chain or there's a piece of cloth that charges up a surface and you actually produce sparks. Well, that's pretty well what our accelerator is. Only we try to avoid sparks, which is why we actually keep this whole accelerator column in a tank that is insulating. And so this actually gives the energy to the particles as we accelerate them. As they get accelerated, again, you have even less of the kitchen sink, and all of these get separated. And so ultimately, if I've set all my system correctly, I can really only see those carbon-14 atoms that I've separated from everything else. And so if all of this works correctly, and if this works well, I can separate out these very, very few carbon-14s. The interest of that is if I now have an artifact, I extract some amount of carbon, I put that through the accelerator, and then I measure the amount of carbon-14 that is now left. Knowing how much I should have had, I can extract an age. Typical example of this is the following. You probably heard about the ice mummy that was found in the Tyrolean Alps, generally referred to in certain ways as Ötzi. He was found about 15 years ago. And he was found here in the what is called Ötztaler Alpen, which is exactly at the division between Austria on this side and Italy on this side. And it was actually determined that he lay on the Italian side, which is why he is now in a very beautiful museum in Bolzano. Anybody going to Bolzano, I strongly recommend to go and see this. So at first they actually thought that it was somebody that had slipped and fallen. It was actually not a mummy. So for the first 48 hours or so, this was not considered an archaeological find, and a lot of people trampled around. Actually, anybody who would have dealt with forensics would have been mad too. So it took about 2 days before they actually discovered that this was several thousand years old, and so they then actually transformed this into an archaeological site. And the first question is what is the age? Again here, carbon-14 would fit very well. Again, the archaeologists weren't too happy about the idea of sacrificing large amounts of their mummy, but milligrams of sample were available. And so 5 different labs at the time, I was at the University of Vienna in Austria, but 5 other labs got various, not only pieces of material from the mummy itself, but of the surrounding equipment. And so what they did is all independently, but they did the same method, which is you take your sample, you burn it, you then accelerate it, you separate out the carbon-14, and then you count how much you have left. And you compare that to how much you would expect. You then have to, and I'm going to very quickly gloss over that, go through what is called a calibration curve. So I initially said that we always expect that carbon-14 was the same in the atmosphere. That is not quite correct. Actually, the carbon-14 concentration changed over several thousands of years. This is in per mil. So it's a very small change, but when you're looking at trying to identify ages that are precise to plus minus 100 years, you need that precision. But so this is actually done by looking at tree rings, counting tree rings, and measuring the carbon-14 in each one of these tree rings. That's how you build up this calibration curve. Once you have all of that, you can actually compare that to some of the equipment. You have the Iceman's body that is actually here, the Iceman's equipment, quiver, frames, and you have the extracted ages, and all of these line beautifully up to about 3000 BC. So we're looking at a mummy that is about 4,800 years old. For those of you that are wondering if this is all connived and if I would take anything, I would get the same age, let me just quickly go on. I'll come back to the other ones. This is some other material that was found all around, but that was definitely, at least archaeologically, not attributed to being the Iceman. So there are leaves and needles, there's high altitude grass, moss, animal dung and feathers that were found. And you can see that actually the range is enormous. Obviously some of them would have fit into there, but the range is enormous. Whereas if you look at the material that is really attributed to the Iceman, the age ranges are beautiful. All of these bars, this sort of what is called the error bar, is because you're going through the calibration curve. But the beauty of this is that with a few milligrams of material, I can actually attribute an age. And I can do that with many other different things. The beauty, and I'd say where the fascination, at least for me, for this is that if you're looking at trace elements, and you use the tools that are, in my case, physics, but it can be chemistry, it can be biology, it can be a lot of different tools. And if you can access that information, you can get a very precise picture, and you can get a very precise piece of the information. Does that mean that it gives me the full answer? No, but it adds some piece of information. If I can access that, I can authenticate works of art by simply finding its composition. I can actually see if the composition is something that could have been used. That doesn't mean that if I find, let's say, titanium white in a work of art that pertains to be several hundred years old, that it can't have been restored at some point. So again, that's where I'm saying it's not the full answer, it's just a part of the picture. But ultimately, these are sort of two techniques that are embedded in, I would say, nuclear physics that allow us to get some very precise information on art and archaeology. Ultimately, this can be used to authenticate works of art. It can help us to understand the history of that work of art. It can give us information on people. If we look at the Iceman, there was an enormous amount of analysis that was done also on the food that was found undigested in that mummy. That teaches us so much about the migrations, where he came from. We know more about the Iceman now than a lot of people that are living nowadays. He was studied in so many details that actually one knows exactly where he was born, how long he lived, all of that. And even all of that was done, it was only years later that they actually found that he probably didn't die of natural death, but they had actually an arrow, a piece of an arrow in his shoulder blades. So again, that goes to show that any amount of analysis still always leaves unanswered questions. That's what makes it so exciting. So, as I said, these are only two in a whole array of techniques. Those are the ones that we work in. And again, I'm no specialist in works of art, especially the authentication. We try to shy away from that. We leave that, but it's the same techniques that they will ask. And the interesting thing is that it's only now that some of these larger cases have come up that there is a whole sort of industry that is starting out around New York City, London, and some of the larger art markets to do real authentication of artwork. It's something that is very surprising. It really has only started now that just this sort of the art historians' comparison of these look like paint strokes from so-and-so are not enough anymore. And they're not enough anymore. They're extremely important. The art historians' information is extremely important. But the forgers, as the forgers get better, we have to dig deeper and deeper and deeper. And somewhere in there is an answer. And we have to be able to access it. So thank you for your attention. I hope I didn't bore you too much to death.
We have time for questions. I'll raise your hand. I'll come by with a microphone. Figure out the best way to, let me come around here.
You mentioned that in your looking into a picture, an artwork, you can go deeper with some of your techniques. So is one able, by going deeper, actually able to tell if a painting has been painted over another painting?
Yes. So I can do that with other techniques too, but we can actually tell the different layers, and I didn't go into detail here, but there's actually detailed work that we've done in various labs, and we have done that too, where you go from one layer to the next, and you can actually see the composition changing as you go deeper and deeper. The only thing that one has to take into account is that as I go deeper, I need more energy. As I need more energy, I'm depositing more energy in the piece of artwork. So again, that's something where a lot of people and a lot of curators tend to get a little bit nervous if you're going to be burning a hole into something. So the answer is yes, but it does come with, you have to be very careful. And so in certain cases, when you really need to go very deep, there are other techniques like neutron activation that will give you an equally good answer. But in that case, it needs actually a reactor, which is not that easy to get at either. But there are other techniques that can take over.
Your talk was very interesting. My question is, if you are not in the business to authenticate art, what do you say after you've looked at a piece?
So, so in our case, what we do, so as physicists, we really only give the composition. So we get this information. I can give an age, I can give a carbon-14 age, or I can give a composition. In our case, as I say, as we don't really work with authentication, the information is mostly of interest for anthropologists that are looking at provenance of a lot of Native American settlements. That they're looking at potteries, they're looking at copper, and they're trying to understand the trade routes, they're trying to understand where these things come from. They have the knowledge, the historical knowledge that we don't. What I can do is I can provide them and I can say the copper that was used in this artifact or in that artifact has this composition, which seems to indicate that it was of European origin or it was of native origin. The interpretation really is to the historian. I can give a piece of the puzzle, but that is the scientific evidence that I got from there. I can't, because I'm not a historian or I'm not an archaeologist, I can only give this sort of factual evidence. How it's interpreted, how it fits into the larger picture is very often not up to me simply because I'm not the specialist.
From a purely practical standpoint, say if you're going to authenticate a Degas, what would the cost be to go ahead and put it through this type of analysis?
So if you're looking at Pixie, our sort of standard costs to operate the accelerator for an hour is about $6,000. That's simply if you take the electricity costs, the maintenance, etc. You're looking at about $6,000. If you're looking at a standard Pixie machine, it would be a lot less, although the equipment itself does come with certain expenses. But that's about what you're looking at. The analysis itself, depending on how many points need to be analyzed and things like that, but one point will typically be about 5 minutes, something like that. I can get a very nice spectrum in about 5 minutes. That'll give me the composition.
Can you speak to the aging of the Shroud of Turin?
I came prepared. Due to lack of time, I wasn't going into it, but yes, let me at least. So it was also analyzed exactly by accelerator mass spectrometry. So I'm going to make it short because obviously I didn't have the time. So I won't go into the history of the Shroud of Turin, but very shortly, it's historically known. It's not very visible here, but 1357 is the first time that it actually appears in various documents. Interesting enough, that is a time when a lot of various religious artifacts were faked. We know that it was then in Lirey, Champagne in France. There were fars, so I'm sort of just glossing over this. This is known history, but the first time it really appears is 1357. So for a long time there was this question, is it the original shroud of Christ? Obviously there is the information that is from the negative positive. One can see the picture of a man, and it actually coincides to somebody who could have been crucified. So 3 labs actually, I'm going to jump over this very quickly. There were a number of samples taken. So there was samples from a Nubian tomb, linen from an Egyptian mummy, and threads from a cope of Louis d'Anjou to do different ranges. All of these were treated the same way as the samples from the Shroud of Turin. Actually, what happened for the Shroud of Turin itself, and I don't have a slide for this here, is so very small samples were taken from a specific spot. They were taken by the curator of the British Museum and a number of bishops from the Vatican. They then cut the samples into and then anonymized them. So 3 different labs, one in Oxford, one in Zurich, and one in Tucson, Arizona, got the samples. They did not know what they were measuring. They simply had them numbered. And the dates that they came up with, here they are, but I think I have a shorter version. Let me see here. No. So sorry, you have all the different samples here and the ages. What you can actually see, so you have the Arizona lab, the Oxford lab, the Zurich lab, and the different samples. And I cannot remember now exactly which one is the Nubian ones, but so they correctly identified all the known samples, and all of them came up with an age around 1350 for the Shroud of Turin. Now, does that answer everything? No. There will still be people who maintain that there's other pieces of evidence that could indicate that it is from that time, from the time of Christ, i.e. there was some pollen analysis done, but the carbon-14 dating was done properly. I mean, I know some of these people, they did it very, very carefully, and so that piece of material that they analyzed clearly comes from the 1300s. Now, there are some people that claim that the FARs may have changed the age. The FAR would really only have made it younger. So it's an interesting case. It's as much scientific as there are a lot of people that are also claiming that, where the place where the sample was taken could have been a place that was restored. It's one of those, you're never going to convince everybody, and it's the sort of standard answer I tell my students is I think that it's rather marvelous that it actually did not date to 2,000 years ago, because ultimately it's a question of belief. And if the Christian belief is not really based on the Shroud of Turin, so ultimately not having a definite answer, but having to rely on faith, I think makes it more interesting. But so, sorry for a long answer, but I thought that might come up, so. But there's a very good article, actually. I think I got the reference here, yes, in Nature, that has all the gory details. I strongly recommend that, actually.
This kind of relates to the Shroud of Turin. Have you ever had a customer, for lack of a better word, that was quite upset with your results or quite astonished with the data that you gave them?
Both. Both. You have people that, we've had a few people that have actually brought in artifacts that were in their families, that they were convinced were very old, and we had to show them that they actually were not. But there are also some surprises, so it's, those things always happen. That's the danger when you go into scientific analysis. You may get an answer that you're not necessarily going to like. And again, it's only a piece of a puzzle. I can't say that it answers everything. Something could have been restored, something could have been... But yes, sadly, some people are very disappointed.
You showed us a chart that had the paints that were used over time. Were your techniques for measurement what established that chart, or was that done?
No, that actually was established, so using mostly, so it's people who are in the business of restoration actually established this chart. I'm trying to find it. It's probably easier if I go it this way. Actually, the reference where it comes from, sorry, I'm nearly there. Here it is. Just doesn't show up, but it's actually, it's published by people who are specifically working in the I can show you this is actually the reference down there. There are labs in both Ghent and at the Louvre that work specifically on restoration of artwork. And they've actually established these. And what they really work on is a chemical analysis of what the different elements are of known paint. So they don't necessarily, you don't necessarily have to rely on the old paints to do that. You can simply look at larger canvases where you have more amount, and then they simply do the chemical analysis. Yes? So this is simply the chemical composition. Oh, this one? Yes, so this is simply, so there are records when specific pigments were used. And so again, this is work that was set up and made by art historians. And there are specific records of when specific a cerulean blue was used, or when a titanium-based paints are modern. So those really have sort of 60 years. Lead white has been used forever. So there are records there, and again, that's why there's a sort of certain fuzziness. There's not necessarily a specific date when a pigment was used, but there's a sort of general range of when a specific pigment was accepted. And that had to do with the availability of the pigments. Some of these are based on materials that were not always available in Europe, and so came later on. Some of these were also due that people remixed paints as some of them became less sort of stable. That was the big secret, and the difficulty was making paints that were stable with time.
All right, thank you, Dr. Colon, for the wonderful lecture.
Thank you.
And thank you for attending tonight's lecture. Remember, Michael Pollan, tomorrow night, 7 p.m. at Unity Temple on the Plaza. And our exhibition galleries will be open this Saturday from 10 to 2. Thank you and good night.